Hey folks, welcome to this episode on reaction quotients. So, what is a reaction quotient? Alright, well, first of all, we know that our K equilibrium is our ratio of products to reactants at equilibrium. So those are our concentrations or our partial pressures or whatever at equilibrium. However, our reaction quotient is very, very similar. If you look here at the bottom, you can see that our expression for K equilibrium is identical to our expression for our reaction quotient, which is shown by Q. So what is the difference? Well, our K equilibrium shows our concentrations at equilibrium, hence the K equilibrium. The reaction quotient isn't as constrained. This shows our ratio between products and reactants at any time during the reaction. Now, this could be at the beginning of the reaction, it could be at equilibrium in the reaction, or it could be somewhere in the middle. However, so this allows us a lot of flexibility. Okay. Now, in this case, this is really, really cool because if we know what our quotient is, we can figure out where our reaction is in terms of attaining equilibrium. If our Q is equal to our K, that means that the reaction is at equilibrium, nothing to worry about. But if it's larger or smaller, it means that the reaction is still progressing towards equilibrium. And that's what we're trying to find out. So once again, our expressions are the same, but the meanings are a little bit different. These are concentrations taken at equilibrium. These are concentrations taken at random sometime during the progress. If they equal the same, the reaction's at equilibrium. If they're not, they're somewhere in progress of attaining equilibrium. So what does the magnitude of Q and K tell us? Well, remember that if we look at K equilibrium, this is our concentration of our products over the concentration of our reactants. And same with Q. Okay? Q is same thing as the concentration of our products over the concentration of our reactants. Okay. So, if our Q is going to be bigger than our K, what that means is the only way that we can get a value that's larger is by having a larger numerator, okay, or a smaller denominator. So what that means is that we've created a lot more products than we should have at equilibrium. Now, one thing you have to know is that for a particular reaction at a particular temperature, there is a known value for K equilibrium. You can open up your Merck index and you can find that K equilibrium value for that reaction at that temperature. So we can open up this book and say, well, for a reaction so-and-so at this temperature, our value is this. If we take a sampling and we see that our Q is bigger than that expected value, and we're sure that it's at the right temperature, what that means is that the reaction is still progressing. It's at a point where it has the concentration of products way too big and therefore has to use them up. So if we look at reactants turning into products and vice versa, in this case products, if our Q is way too big, it means we have a lot of products. They have to be converted into reactants to finally get this ratio that is expected for the reaction. Now the reverse is true if Q is less than K. For Q to be less than K, that means that our denominator is going to be really, really, really big. And that makes a small kind of decimal number. What that means, again, is that we don't have the correct ratio of products to reactants as we expect for that KQ of that reaction at that temperature. So our reactants are in the progress of finding the equilibrium, which means that they have to be used up and create products to get that ratio over here. Now, a thing of beauty is if K and Q are equal to one another. And if so, that means that the proper ratios of products to reactants have been reached, and it matches what our K equilibrium is for that reaction at that temperature. So let's look at our first example here. Here we have hydrogen reacting with iodine to produce hydrogen iodide, and in this case we are given our equilibrium constant. This is 7.1 times 10 to the 2. This is our value for K equilibrium for this reaction at 298 Kelvin. If the current concentration of gases are as follows, what direction will the reaction shift to reach equilibrium? Okay, so our K equilibrium expression is going to be the same as our Q, our reaction quotient expression. It's going to be the concentration of our products raised to the power of their balance coefficients divided by the concentration of our reactants raised to the exponent of their balance coefficients. So our product in this case is HI gas, and that's going to be to the power of 2, over concentration of H2 gas multiplied by the concentration of I2 gas. Okay, now if we plug in our values here, HI is going to be 0.58 molar times to the power of 2 over H2, which is going to be 0.81 molar multiplied by 0.44 molar. Now if we work this all through, we get 0.94. Now let's bring that into scientific notation just to make it a little bit easier to compare. That's going to be 9.4 times 10 to the negative 1. So let me write these down here. Our K equilibrium is given, and it's going to be 7.1 times 10 to the 2, and our reaction quotient is 9.4 times 10 to the negative 1. So what we can see here is times 10 to the 2 is obviously bigger than times 10 to the negative 1. Our Q is bigger, our KEQ is bigger than our Q. Now what does this mean? Well, for our reaction quotient to be a smaller number, what that means is that we have a lot of reactant. Okay? Our ratio is very reactant heavy, which means that we have to move from reactant into creating product to establish the ratio as expected in this reaction at that temperature. So in order to do this, in order to use up some of this reactant, equilibrium has to shift to the right. Okay? It has to move from the reactant side to the product side. All right, let's look at our second example here. In this case, we have carbon monoxide reacting with steam to produce carbon dioxide and H2 gas. So at a given temperature, it doesn't tell us the temperature, the equilibrium constant is 1.0. This is going to be our KEQ. So again, something to reference. If these are our concentrations at some random time, or the current concentrations, which way will this reaction have to shift? Now, just because the question says it has to shift, it doesn't necessarily. That's what we're trying to find. If Q is larger or smaller than K, then it will have to shift. But if it's equal, then it won't. Now, a little note on the nomenclature here. We have these little zeros by the concentrations, and these mean that these concentrations have been taken at a random time, at a time that is maybe not known that it's equilibrium. Okay, so these concentrations could be at equilibrium. They could not. They maybe not are not. They're just taken at a random time. So what we have to do is find our reaction quotient. So again, products over reactants. Concentration of CO2, in this case gas, multiplied by H2 gas over concentration of CO gas multiplied by H2O gas. Okay, so we sub in our samples here. So CO2 is going to be 2.0 molar multiplied by H2, which is 2.0 molar, divided by 1.0 molar multiplied by 1.0 molar. So if we do this all out, we get 4.0. Okay, and that's our Q value. So once again, our Q is going to be 4.0, and our K equilibrium is going to be 1.0. Now, again, this is pretty obvious. Our Q is going to be bigger than our K equilibrium. In order for this to happen, what that means is that our numerator is a lot bigger than our denominator, which means we are product heavy. So right now, we're lying somewhere over here, and we need to get to an equalization point, which means that we have to convert some of our product into our reactant. So right now, because we have a large number, we have a lot of products, and we have to convert that into reactants. That means that equilibrium has to shift to the left. And that means towards the reactants. Okay, here's our last example. We have HCl gas plus NaOH aqueous reacting to form NaCl aqueous and H2O liquid. So here is our constant for the reaction. KEQ is 0.5, so once again, I'm just going to highlight that's KEQ at a given temperature. Temperature is not given. If the current concentration of the gases are as follows, what direction will the reaction shift to reach equilibrium? Okay, now right away, you should see something. when it comes to looking at our quotient expression, it's products of reactants. However, look at the water. The water is a liquid. Now, if you didn't see that, you should have seen that there's only 3 values given to us. We do not have a value for water because these liquids are incompressible and they are not going to be provided or included in our equilibrium or reaction quotient expression. So our expression is products of reactants, in this case our concentration of NaCl, and that's aqueous, divided by our concentration of HCl gas, multiplied by NaOH aqueous. Now just to quickly go over, make sure that these are all balanced. 2 Cl, Na. Good. So everything's balanced. So that means that our coefficients in our balance equation are all 1, and the exponents are also going to be all 1. So let's plug in our values here. Our values are all in mole per liter, so we can just do a direct plug and play. We get 7.0 molar to the power of 1 multiplied by 5.6 molar for NaOH and 2.5 molar for HCl. So if we do this through, what we get is 0.5. So our Q is 0.5. So our Q is 0.5 and our KEQ is 0.5. Well, look at that. They're equal. So what this means is that this sampling, even though they were denoted by zeros, are actually taken from a reaction that's currently at equilibrium. So this reaction is at equilibrium. It doesn't have to shift left. It doesn't have to shift right. It is where it needs to be. Thanks very much for watching. See you next time.